All right. Good morning. Good afternoon. My name is Mr. Mlenga Kunda, the science and mathematics teacher at the Our Lady School in Lusaka. For those that have been following me on YouTube, I've been producing a series of videos in various subjects such as mathematics, chemistry, and yet to do physics, among others. Today, we will be looking at chemistry. So today, we'll be looking at chemistry. Now, many people have approached me saying chemistry is very difficult. No, I beg to disagree with that. Chemistry is very simple. What makes people say chemistry is difficult? It could be that they miss certain components, and among them is what you'll be looking at today. If you miss this component, you find that you have difficulties down the line. So today, we'll be looking at the radicals and the valences. Today, we'll be looking at radicals and the valences. Then later on, we'll look at the chemical formulae. So to start with, it becomes difficult for us to start looking at something that people don't know. Even us looking at something that we don't know, it is quite difficult. So the best thing that we're going to do is we're going to understand the meaning of these two terms, valences or valence, as well as a radical. What is a radical? A radical is an atom or group. Groups, atom or group of atoms, that exist in many compounds. But are incapable of independent existence. Yeah, that's the definition of a radical. A radical is just can be an atom or can be a group of atoms. These atoms, they exist in several compounds as well as molecules. Compounds rather, but they are incapable of independent existence. What does it mean? They cannot exist on their own. If you're walking around the street, you find a radical, run for your life, because that has never happened from the existence of the world. So having looked at the definition of a radical, we're going to look at roughly at what a valence is. So we're going to look at a valence. A valence, there's too much ambiguity on the definition, but I'm just going to give you a very short and a brief definition. A valence, we're going to call it combining power. It's a combining power of an element. Combining power of an element or radical. Combining power of an element or radical. Why are we saying the combining power? Because the valence of an element or the valence of a radical is what it determines how many other aspects will be attached to it. We'll look at much more of it when we go a bit further from this. So radical, the valence is just a combining power of an element. So from here, I'm going to give you a table. I'm going to give you a table which consists of the radicals, their chemical formulae, as well as the valences. give you the table that you have the radicals. We also have the chemical formula of such radicals, and then I also give you the valence that each radical has. I'll just give you some few. So this one here will have, if you can allow me to get to the other side of the board, I will have radical, then I will have chemical formula, chemical, let me do this, I will have a bit bigger, I'll have a radical here, then I'll have chemical formula, I will also have the valence. Ma disturbance ega chape. Bazaba kunzise babwezi. I'm okay, how are you?
I'm okay also.
You can allow me to continue?
Yeah, continue. Can I tell you on?
Not pausing a chape. All right, so the table that we're going to have, we're going to have that table which will have the radicals, in words that is. We're going to have chemical formula of such radicals, and then we also look at the combining powers, which we are calling the valence. Now, remember what I said, a radical can be a single atom, can also be a group of atoms. So I'll have them combined, but basing on the number or basing on the valency that they have. So the first bond, let me also put a serial number here. The first bond that we can look at is chloride. Chloride is a radical. And then the chemical formula of the chlorine or chloride rather is Cl minus. Cl minus whose valency is 1. So I can say from here that chloride is a single atomed radical. It's a single atomed radical. The other one you can look at is nitrate. Nitrate, whose chemical formula is NO3 with a charge minus. So the valence for nitrate is also 1. The other one is, we can look at ammonia, NH4. Oh, ammonium, in words. We're going to have ammonium, which is NH4 plus. The valence is 1. I'll give you just 2 more. The other one is hydrogen carbonate. Hydrogen carbonate, which is NCO3 minus. Hydrogen carbonate, the valence is 1. The other one is hydrogen sulfate. Hydrogen sulfate, which is HSO4 minus the valence. Yeah, so among others, these are the few radicals that I'm going to talk about, whose valence is 1. So you look here, chloride, the valence is 1, nitrate, NO3, and the valence 1, ammonium, NH4, the valence 1, hydrogen carbonate, HCO3, valence 1, hydrogen sulfate, HS4, also has the valence of 1. So these are a few radicals that we are going to have for now, whose valence is 1. Now let's go to the other set of the other set of radicals, those that have got the valence of 2. Those that have got the valence of 2. So if you want to write it down, you can pause the video and then you have it written down and resume later. So the other one that we're going to look at, the other set of radicals are those that have the valence of 2. Those that have the valence of 2. But I'm not going to give you a lot, and many others will find them as we discuss and then the following items. So the first one, those that have got the valence of 2 is carbonate. Remember, the one that we had at first was hydrogen carbonate, but this one is just single carbonate, whose valence, whose chemical formula is CO3 2 minus. Indeed, the valence is 2 carbonate. The other one that we're going to look at is an oxide. An oxide whose chemical formula is 2 minus. Oxide. Okay, oxide, which is like that, which is O negative 2, and then the value is 2. Then maybe for now, the third and last one that we're going to look at is the sulfate. The sulfate, whose chemical formula is SO4 2 minus, and the valence is 2. What can we learn from here? We can see that all these three that we've itemized right over here, the charges negative 2, negative 2, negative 2, therefore their valences is 2. You can also look at sulfide, which is S2. You find that the valence is 2. If I'm to put it here, but I'm not going to do it. Yeah, these are the ones that for now we're going to have. Then after this, we're going to look at those that have got the valence of 3. Valence of 3, but I think I'll just make mention of 1. I'll just make mention of 1. So this one, which has got the valence of 3, is called phosphate. Is called phosphate.
I seem to get a
By who?
Mr.
Don't you know that you are disturbing?
Sorry, sir.
I'm punching on the chest. Mr. Power is one who's going to feel pain. And the what?
Triangular prism.
And what is your mother saying?
Eh,
You have no comment. That's the one, triangular, right? Not rectangular. That's a triangular. Is it triangular or rectangular?
Rectangular prism.
Which one? You see? You're lost. So let me give you both. Then this one is a rectangular. The one we are using, that one's a
The
triangular.
one for dispersion is
Say that one, say wait. So that you look like you don't know.
After my series is on, you are almost done, isn't it? Because if I'm almost there, so you're starting.
No, I'm just pausing.
Okay.
What was I talking about? Okay. Yes, so this the sulfate and the phosphate rather, the chemical formula is PO4 3 minus. And from the charge here, we can depict that the valence is 3. Okay, so we've looked at those that have got single valence, the nitrate, the chloride, the ammonium, the hydrogen carbonate, the hydrogen sulfate. Then we also looked at those that have got the valence of 2, the carbonate, the sulfate, the oxide, among others. Then this one just got the valence of 3, which is the phosphate. Now, why are the valences important? Because right from here, we'll be looking at how to construct chemical formula. If you don't know the chemical formula for the radical as well as its valence, it becomes difficult for one to construct the chemical formula. If you don't know how to construct the chemical formula, it will be very difficult for you and I to know how to convert a word equation to a chemical formula, because from a word equation to a chemical formula, from a word equation into a chemical equation, because a chemical equation will consist of this, the chemical formula. And if you don't know that, it also becomes very difficult to start looking at the stoichiometrical calculations, such as the number of moles, the molar mass, and things like that. Okay, so let me give you now a brief introduction of the chemical formula. The brief introduction of the chemical formula, and thereafter we're going to look at how we can construct chemical formula. Many students that have difficulties on how to construct chemical formula. One, it is because they don't know the radicals and their valences. Not on that, others, it's difficult to tell the valence of elements from the periodic table. So I'm going to give you some tips on that. So what we are saying is chemical formula. A chemical formula. This chemical formula will consist of the symbol of the combining elements of radicals, as well as the it is going to consist of the chemical. To consist of the chemical symbol, not only symbol or symbols of elements. That are present in one mole of a compound. One mole for now, maybe you may not understand what a mole is, but as time goes by, you're going to have ideas on what a mole is. So we're saying chemical symbol consists of chemical formula consists of a chemical symbol. It may be a symbol or of elements. Symbol or symbols of the elements that are combining in forming one more of a compound. So that reminds us to say you need to have the symbol of an element or elements that are combined with the elements that are combining with radicals in forming a compound. Yeah, it's very important that you understand them. Now, because we said valences are combining powers of these, so therefore we need to understand every element that you pick on. You should be able to tell its valence, because if you don't know its valence, I can assure you it's going to be difficult for you to write the chemical formula. So now let me give you 3 steps. These 3 steps are very important. These are the ones that will guide us on how to write the chemical formula. I think that's where we're going to end for today. So the steps that are involved, these steps are very important. Steps in constructing chemical formulae. Formula 1, formulae, more than one problem. Now, the step number 1 is that you need to write the symbols, or you need to write the symbols of these elements or radicals that are combining. You need to write the symbols of elements or radicals that are combining. That's the first step. You need to write this. You need to know how to write the symbols of the elements or radicals that are combining. You write them separately. Yeah, so I'll give you examples of this. You can have maybe calcium as an element combined with a radical, which is sulfate, in forming the compound called calcium sulfate. Or you can have an element such as aluminium, which is combining with a radical, which is phosphate, in forming a compound which is called aluminium phosphate, among others. Okay, so the second step is that you need to write these symbols. You need to write these symbols separately, even here. Then you need to distribute their valences on their top right. You need to distribute their valences on the top right. So you're saying after you write these symbols separately, as you wrote here, then you need to write. You need to write their valences. You need to write their valences on the top. On top right hand side. Sorry. First step, you write the symbols, elements, and radicals. The second step is you rewrite them the way they were, then you distribute their valences on their top right. Then the third point is now you have to combine these elements, their symbols and radicals. Now, when you combine them, you need to interchange their valences. You need to interchange their valences. You write them now as the subscripts on the right hand side. So now you need to interchange their valences and have them combined. Then you interchange the valences. So you're saying you need to interchange their valences. Need to interchange their valences and write a subscript. And write them as a subscript. So these are the three important steps that we're going to look at for today. That's where we will end. 3 steps when constructing the chemical formulae. First step, write the symbols of elements that are combined with the radicals. Write them separately. The second thing is rewrite them, then distribute their valences on their top right. The third point is once that is done, then you are going to interchange them. But be reminded that if the valence is 1, you don't write it. If the valence is 1, you do not write. And then when you're interchanging the valences, if if you find that the radical has more than 1 atoms, when you're writing that radical that valence as a substitute, you make sure that you put those radicals and the brackets. I'll give you tips, or I'll give you look at them during the examples. So you need to pay attention to this. I'm not going to drop those steps because those are the ones that I will be looking at. So the example, which is the last part for today, the examples, write the chemical formulae, the formulae of each of the following. So number one, we're going to look at potassium carbonate. You look at potassium carbonate, which in words is written as potassium carbonate. But we just looked at how to depict the carbonate, which is the radical. There's a table that we follow. But what about elements such as potassium, which is a metal? Any element after a radical configuration, if the number of electrons in the outermost shell are between 1 and 3, that is equal to its valence. If an element after a radical configuration of the atomic number, if the valences, the number of electrons in the outermost shell, which we call the valence shell, the valence electrons, if they are from 1 up to 4, that is equal to its valence. But if an element has got electrons in the outermost shell for non-metals from 5 up to 7, you make sure that you subtract that number from 8. If an element such as oxygen has got the number of electrons in the atom shell, which are 6. So get that 6 and subtract from 8, that will give us 2. That's why the oxide has the valence of 2. The other one that we can look at is the chloride. The chloride, which is in group 7, has got the atomic number of 17. So if you put them in the configuration, you're going to have 2, 8, that is 10, and 7, because number of electrons in the atom shell are 7. You subtract from 8, you're going to have the answer, which is 1. That is why chloride has a valence of 1. So with all that said, let's see how we can construct the chemical formula for potassium carbonate. The steps are very important. Potassium is written as K. Too much ambiguity. Instead of having K or P for potassium, but P is used for phosphorus, we use K, which is driven from a Latin name. Then the carbonate we wrote is CO3. First step, we've written the symbols. Then the second step, we said we write these symbols and distribute their valences. So because potassium is in group 1, therefore the valence is 1. So we're going to say K with the 1 here, then the carbonate 3 with a valence of 2. We said must be written on the top right hand side. Then the second step is you just need to combine these entities. When you combine them, then you interchange the valences, and if the valence is 1, so meaning the 1 which is on the potassium will not appear on the carbonate, because if the valence is 1, you don't write it. Therefore, the chemical formula for potassium carbonate will be K, whose valence now, this 2 which was here, is going to be written as a subscript on the potassium, then the carbonate, because on the potassium the valence is 1, therefore we're not going to write it. That is the chemical formula for potassium carbonate. Potassium 1, carbonate 2. So you're going to interchange the valences. Okay, so the other one will be aluminium phosphate. So this is 1. Then the other one will be aluminium phosphate. So the aluminium phosphate, which is 2, aluminium phosphate. Sorry about that. So the aluminium phosphate, if you look at the aluminium, which is written on the periodic table, the nuclear notation is Al 27 and 3. So that 3, which is atomic number, it is there to help us identify the valence. We are saying the valence for elements such as aluminium, we write the configuration. The first shell 2, the second 8, the third one will have 3. Therefore, the valence for aluminium is 3. But we're not going to write the valence for now. The phosphate is a radical, which we've looked at. So the aluminium is Al. Then the phosphate is PO3. So the second step, we're going to write them with their valences. So the aluminium is Al, then the phosphate PO3. But if you go back to the radical table, we find that the phosphate has the valence of 3, aluminium also the valence of 3. So when we interchange these valences, you're going to have Al, this 3 now comes here, then PO3, the PO3. But because we have another 3 coming now to be written as another subscript, we're going to write it like that. But you can see that the 3 and the 3 can be cancelled. So therefore, if you divide by 3 here, also divide by 3 as the smallest number to reduce them, and the chemical formula will be AlPO3 with the 3's disappearing. So don't get confused that this 3 is the valence for aluminium. This 3 is part of the phosphate radical. Okay, we look at 2 more and then we're done. The other one is many times we know that carbon dioxide is CO2. But how does it come about? So carbon dioxide is CO2, water, which is H2O. We're going to look at how water is written H2O. Why not H3O? Okay, so we're going to look at that. The third one is we can look at carbon dioxide. Carbon, which is a metalloid, has got the symbol C. Then dioxide, it means we're talking about oxides, which are two. But where does the two come from? We are not, the dioxide is not a radical, we're just interested in the oxide. Remember on the table that I gave you, there is no dioxide or monoxide, because these are just prefixes that are there to tell us the number of radicals that are there. So the radical here is the oxide, which is O. But now pay attention to this. The oxygen here, the oxygen is in group 6 because it has got 8 electrons. So when you write the configuration of this oxygen, the first shell will have 2, the second shell will have 6 because there are 8. So 6 is not a valence. We subtract this from 8, we're going to have 2 as the valence. Carbon, I said if an element has got the electrons from 1 to 4, the number of electrons in the outermost shell is equal to the valence. So the carbon is written 12 and then 6. So if you do the configuration, the first shell 2, the other shell 4. So therefore the valence is 4. Okay, but now we're not going to do the valence on the initial stage. Okay, so the second stage is now you write these symbols with their valences written on the top. Then thereafter you interchange. You're going to have C. Now this which was here will come here, and then all this 4 which was on carbon goes on oxygen. But we are very not sure that there is a number that can reduce these two guys. So if you divide here by 2, that the valence here becomes 1 after the valence is 1, you don't write it. So therefore, we're going to have carbon, then carbon, the valence is 1, I'm not going to write it, then 2 into 4, that is 2. So that's why carbon, the combination of carbon and oxygen to form carbon dioxide, this is how they arrived at that formula. All right, now we're going to look at water. Water, which is a combination of hydrogen and oxygen. Water, which we call dihydrogen monoxide. The fourth one, water, also called dihydrogen monoxide. So we're going to see how that happens. So it's this molecule is formed by the combination of hydrogen and oxygen. First step, these are the symbols, but hydrogen is in group 1, therefore the valence is 1. So we're going to have hydrogen the second step with 1. Then oxygen, which is in group 6, has got the other one is in group 6. So subtract from 8, you're going to have 2. So these are the valences of hydrogen and oxygen. Now when we combine them, having the final stage, we're going to have the interchanging of valences. So this 2 gets to be here, and then the oxygen is going to bear a 1, but when the valence is 1, we don't write it. That's why water is written as H2O. The last one is, I've tried to put it here because it's a little bit confusing, which involves the putting of radicals inside of the brackets. The last one, which is the fifth one, is the fifth one is aluminium. Carbonate. The one that we have at first was aluminium phosphate, whose valences for both was 3, and therefore they cancelled out. So aluminium is Al, the carbonate a radical CO3. The valence for aluminium is 3. The valence for carbonate is 2. Where is the 3 coming from? Remember, I just wrote the configuration of aluminium, which is written as Al2713. So when you do a configuration of this, the first shell being 2, there are 13, we are remaining with 11. Then the second shell gets to have 8. When you combine these, we get to have 10. But there are 13, therefore the last shell gets to have 3, and its valence becomes 3. Then the third and the final stage is to combine these and interchange their valences. We're going to have a L, but the valence here is 2, so the 2 gets to be on the aluminium. Then the carbonate, which is CO3. But we already have a 3 on the carbonate, and the 3 has to be subscript. We cannot have a subscript of another subscript. And because this 3 is not only for oxygen, therefore we're going to write it as that. So we're going to have di-aluminium tetracarbonate. That's aluminium carbonate, di-aluminium, and the 3 carbonates, di-aluminium tetracarbonate. Many times students get confused, where because this 3 is standing for everything, they are going to say 2 to Al. No, 2 is for aluminium, and then the 3 is for carbonate. No. That is very, very wrong. We don't write like that. These valences, therefore, must be written as a subscript